The tools used for making the parser are Ubuntu version 15.04, and we are using Flex and Bison, which are the Ubuntu implementations of tools Lex and Yacc. Before going through this video, we should have some prerequisite knowledge. Firstly, we will see what are Lex and Yacc. Lex stands for Lexical Analyzer Generator, and Yacc stands for Yet Another Compiler. These are the tools which are used for compiler construction. Now we will see what is front-end analysis. Front-end analysis consists of three parts. First is lexical analysis or scanning, which will be done through Lex. Secondly, syntax analysis or parsing, which will be done through Yacc. And thirdly, semantic analysis, which will not be covered in this video. You must be familiar to regular expressions and some basic Python expressions.
Now, let us proceed towards our Lex program. A Lex program basically has three parts. First is the definition or the declaration part. The second part is the part for rules and actions, and the third part, which is the user subroutine part, has not been used here in this program. The extension for a Lex file is .l. The definition part that we have written in our Lex program is exactly retained in our C file. That is, when we compile a Lex program, the file so formed after the compilation is lex.yy. Now, let us move towards the rules and action part of our code. The rules part is initialized with the help of a %% sign. The words that are written in the double quotes are exactly matched with the input. Here, we are matching the string print, and as soon as this string is encountered, the token print is returned. Now, the question arises, how Lex file will get to know that print is a token? For this, we need to move towards the Yacc file. Here, we have already defined that print is a token, and Lex file is related to Yacc file through the header y.tab.h. Similarly, we are trying to match the Python keywords so that they cannot be used as an identifier by the user. Moving to the next step, we match the numbers using the appropriate regular expressions, and similarly we are doing for the identifiers. Matching the special symbols, they are preceded by a backslash, and then the symbol is mentioned, and there we will return the tokens corresponding to them in each of these steps mentioned here in our code. String literals and variables are string constants handling double quotes and single quotes respectively. Both these quotes are commonly used in Python expressions as it has been shown here in this text file. These strings end with a double quote or a single quote and end with them as well. Here, one needs to make sure that within the quotes we do not mention another quote or a new line. Except these two any of the other characters can be written one or more number of times. Now, further moving towards the dot operator, if any of the operators except for those mentioned earlier in the code is encountered, it will print unidentified token followed by that illegal token which is printed by YY text. After that, we halt our execution and exit with status 1.
Now we are moving towards the Yacc file. On compiling the Yacc file, we get another C file named y.tab.c. As we saw in Lex files, in Yacc files also, the definition portion is retained exactly in the C file. The stdio.h are the header files added for using the input-output features of C files. The macro border increases the readability of the input-output. The YY_debug variable has been initialized to use the debugging features of the Yacc tool. You must remember that in the Lex file, we saw a lot of tokens which were being returned. All those tokens are defined here in this Yacc file. This portion of the Yacc file is used to resolve the precedence in case of an ambiguous or a complex expression. The tokens on the same line have equal precedence, and the precedence increases as we go downwards. So here the tokens MUL and divide have the highest precedence, followed by PLUS plus and MINUS minus and EQ with the least precedence. Thereafter, the percent left shows that the associativity is from left to right, and percent right shows that the associativity of this token is from right to left.
Now let us move on to the grammar part of the Yacc file. The grammar part starts with the start subroutine, which states a statement which is terminated by semicolon. Now we have handled three types of statements of Python here in this program. The first is the arithmetic assignments. The second is the assignment of a string literal to a variable. And third are the display statements, namely print and printf. After the initial syntax of the file is proven true, we print the statement, this is a valid Python expression. After that, we print the border for a little user readability, and thereafter the function YYAccept accepts the syntax. Now let us move on to the first type of statements, which are the arithmetic assignment statements. Now a arithmetic statement is essentially an identifier is equal to some expression. Now the expression can be of many types: expression plus expression, expression minus expression, expression multiply expression, or expression divide by expression. Further, expression can be a single factor which does not break into further parts. Also, expression can be enclosed within the brackets. We can see all the examples in the readme file, where it is the identifier is equal to factor, it is the identifier is equal to expression, and it is the identifier is equal to expression which is enclosed in the braces. Also, in expression we have treated a sign factor, which is a mere case of variable is equal to 5. Now we can see that a is equal to 5, but it might be possible that a is equal to minus 5. So to handle the sign of the integer, we have used a sign statement here. A sign is then broken into a plus or a minus. Also, a factor can be either an identifier or a number. As we see here, a is equal to rod, which is essentially identifier is equal to factor, and the factor is then further broken into an identifier. So all these statements are handled by our arithmetic assignment statements. Now think about identifiers, which is worth noting is that identifier cannot be a keyword. So we have handled the case of keywords, and whenever identifier is used as a keyword, we return the error message. Keyword cannot be used as an identifier, and then we abort the further syntax checking and return to parse as status 1. Now let us move on to the second type of statements, which are the assignment of a string variable or a string literal to an identifier. We move on. Now the statements of a string assignments can be identifier is equal to strings. Now strings can be of two types. Either it can be a string literal or it can be a string variable. These both things are essentially the same. The difference is in double quotes and single quotes. In Python, both the single quotes and the double quotes are allowed. So to handle the double quotes, we have used the term string literal, and to handle the single quotes, we have used the term string variable. So basically these both have the same regex. The only difference occurs in handling the double quotes and the single quotes. Now we move on to the third type of statements, which are the display statements. Now Python supports a large variations in the display statements, but we have handled the major four cases of Python. The first is the print keyword followed by any string. Now we have handled that a string can be either in double quotes or it can be in single quotes. As we can see here, Python supports a string in single quotes as well as in double quotes. Thereafter, moving on to the second part, we can see print keyword followed by string multiply by a number. As we can see here, Python also supports print keyword followed by a string multiplied by an integer. The result of this query is the display of hello 5 times consecutively. Thereafter, moving on, the print statement followed by strings plus strings. This essentially concatenates both the strings. So Python supports the concatenation of two strings by the use of plus sign. Thereafter, we move on to the third statement, which is print with an expression. Print also supports the display of an expression. As we can see here, print 3 plus 2. The relative answer of this query will be print 5. So these four type of statements are handled by our code. Now we move on to the subroutine section of the Yacc file. We start with the Python expression parser and take up a Python expression from the user. Then we call parse, which checks the syntax for each statement entered and returns either it is a valid Python expressions or return the correct error corresponding to it. The error passed is handled by the function error declared here. The function error accepts the error string and then displays it to the console. Thereafter, the function wrap tells the program to wrap up and finish the syntax checking. Now let us move on to the execution part. Now we move on to our project directory, which contains currently two files, which are pro.l and pro.y. So first we compile the Yacc file using the command Yacc -d the file name. Okay, this compiled. Now we compile our lex file. Oh, let us first see what is being generated. Now we have generated the two files here, which are y.tab.c and y.tab.h. Now the y.tab.h is that file which we included in our lex file. As we can see here, we have included y.tab.h and it contains the definitions of all the use tokens from the Yacc file. So let us again switch to terminal. Now we compile the lex file using the command lex.filename. Okay, the files are, now we see what is being generated. The generated file is lex.yy.c. Lex is basically the lexical analyzer generator. So this is our C file, which is the main analyzer. Now we have to compile the two C files obtained, namely y.tab.c and lex.y.c. So we compile and link them using the command gcc y.tab.c lex.yy.c. Now as we can see, the generated application file is a.out. We execute the a.out file and we can see the output on the screen, which is Python expression parser, and it waits for the user to enter a Python expression. Now we enter an expression, variable is equal to -6, and this is a perfectly valid Python expressions as we have handled the sign in our Python Yacc file. Now we'll test various test cases here. All are working fine. Now we test some print statements. The print statements are also working fine. Okay, all the cases that we have handled in our print statements are working fine. As we see, the application file a.out is our Python expression parser, and it basically do all the work that we designed it for. But what about if you are stuck in a problem? For that we have to use some debugging tools. So we are going to learn a few debugging tools. As you can see, we have used yy.debug to 1 in pro.y to enable the debugging features of Yacc tool. So we debug it by --debug and --verbose and file name. So as we see here, we have generated the file y.output. When we open the y.output, we can clearly see the grammar made up of all the statements, and thereafter all the terminals, all the non-terminals, and all the used states in our grammar. This is the finite automata. For more information on finite automata, you can use Google. The finite automata basically consists of an initial or the entering stage, final stage, or there may be a number of final stages, and the transitions. So basically what we do in a grammar is define the transition. Okay. Now we compile it raw dot using L, then we'll link both the files. This is the same thing we have done initially, but there comes a minor difference in the application file. When we execute our application file, it shows us the exact state of the stack. So when we enter an identifier, it identifies that it is an identifier and waits for the next token. When the next token is an equal to symbol, it treats it as a good syntax. Thereafter it waits for the another token, and if we enter a wrong token, the syntax does not match and there occurs a syntax error. Thereafter the stack is cleared and the look ahead token semicolon is also cleared. This may seem a bit complex at first, but when you face a problem, this is the most helpful tool feature. It helps you to debug and show precisely the current stack states. Okay, so that's all for this video. Thank you for watching.